Okay, today we're going to work out the 2017 AP Physics V Mechanics FRQs. On this video, I'm not going to work them out step by step. Those will be other videos, but I'm just going to talk about setting them up, and when you read a problem, the key things to look at to say, where do I start, what do I do? Because with the modifications in the AP exam this year, you have 45 minutes for FRQs, and that's it. So question number one from the 2017, first of all, you're going to look at the picture. So you see two different masses. So the first thing you need to say to yourself is, which way is it moving? So if you read the problem, so it's an Atwood machine, and it consists of two blocks connected by a light string that passes over a frictionless pulley. So that's good because we don't have to worry about like the moment of inertia or anything like that of the pulley, of negligible mass. So the masses of the two blocks M1 and M2 can be varied. M2 is always greater than M1. So the first thing you're going to say to yourself is that M2 is greater than M1, so you can see which way it's moving and which way it's accelerating. So I would draw my sign convention right on here. I would say this is positive going down and this one is positive going up. I'm not writing on these because I'm going to write on them tomorrow when I record them step by step. So remember, if there's one rope, there's one pulley. So because this doesn't have a moment of inertia, because it's massless, the tension is the same. So that means they're equal and opposite because there's no tension in the pulley, so there's no rotational inertia. And that's going to make a huge difference. Now, one of the things that they want you to do in this is you cannot do it as a system, okay? So first of all, what you're going to do is you're going to apply Newton's second law on each block. So first they ask you to draw the free body diagrams. So again, remember that because there's a scale here, what you need to do is you need to make sure, because M2 is greater than M1, that weight, remember, free body diagrams only show the forces acting, nothing else. So you're going to show that this force of M2 is going to be greater than M1. So you have to make this arrow longer than this one. And then the tension is the same, so you're going to make the tension the same. Okay. So you're going to be applying Newton's second law. And remember, you're going to say summation of F is equal to MA. So for block 1 here, remember, you're going to draw your sign convention. Block 1 is going up. I'm going to say summation of F of Y is equal to MA. Then I'm going to look at my free body diagram, which I didn't do, but I'll just do it right here. You're going to have the tension here in block 1 and then M1G. So now what are all the forces acting on this? Well, I know the tension is positive because that's the way it's moving. Minus M1G is equal to M1A. So this is one equation. For the second one, and I'm going to work this out in detail tomorrow. Again, you have your tension, but here this M2G is going to be longer. So then you're going to apply Newton's second law again. Now my sign convention is down because down is positive. And I'm going to say summation of F of Y is equal to MA. Remember, this is M2A. I look at the diagram. That's positive. So it's M2G minus F of T is equal to M2A. So basically, I have two equations and two unknowns. So there's different ways algebraically that you could solve for it. And they even tell you what the answer is there, A. So you're going to end up solving for A. All right. Then this part is a typical AP question. So now you have data, and then you're going to have to do a graph. You know, once you do the graph, you're going to do a best fit line, and then you're going to calculate the slope. Now this one, we did this one already, but this one, remember, you have to look at this and indicate which quantity should be graphed to yield a straight line whose slope could be used. So you have to go back to the equation that they gave you here. A is equal to M2 minus M1 over M1 plus M2, which you derived. And you have to look at this and figure, how is this going to be a straight line? So there's different ways to do it. You can rearrange it to get y over x. Remember that the equation of a straight line is y is equal to mx plus b. So we would have a is equal to m2 minus m1 times g over m1 plus m2. So I can see that this is the slope and this is going to be x. So after you do that, and again, they like to ask these all the time, you're going to put what those quantities are. You're going to then put in here what you're going to graph, and you're going to plot the points to a best fit line with a straight edge. And then here for the slope, remember when I say determine G, well, if G is the slope, which is the change in Y over the change in X, I need to move over. Then don't forget to write y2 minus y1 over x2 minus x1. You want to make sure you want to get every point. All right, so that's the first FRQ. The second, oh, this is the third part of that. That's a long FRQ. So then this one, so now it's on a table. So it no longer is supported by the string. So then they ask you stuff, so the tension is going to be less. So then they ask you about certain things. And then they ask you something about friction. All right, so I'm just going over these real quick, and then I'm going to go over them in detail tomorrow. Because don't just go on the College Board website and copy the answers. So the second one, you have a block here. It starts from rest. That's important. It's at the top of the incline. And the block travels and it makes smooth transitions and everything else. So first of all, before I even look at this problem, there's a couple of things I'm going to think about. First of all, if it starts from rest here, remember, whenever there's a change in height, I can use conservation of energy. Then I have a spring, and there's two things I know about a spring. I know that the potential energy stored in a spring is 1/2 kx squared. And, because I'm using conservation of energy, I'm probably going to end up using that. So basically for this one, the total energy at the top here is going to be equal to the energy. So the total energy here, which is gravitational potential energy, mgh, is equal to the energy here, which is equal to the energy here. Okay, so you're going to use conservation of energy. Then for part D, so there's a bunch of different parts here. It says determine the maximum compression of the spring, which is X, and determine the time it takes. Now, on this year's test, they're not doing oscillations. So there's part of this when we talk about oscillations, because it would be a spring block oscillator, we don't need to know that for this test. So, the period of a mass on a spring, T is equal to 2 pi times the square root of m over k. We're not doing simple harmonic motion on the AP test, oscillations. Now, we are doing resistive forces. So it says derive an expression for the maximum, or we already did that. So D, right, but do not solve the differential equation. So remember, for this, if there's a resistive force is drag. So again, in this situation, whether it's like a block or whatever, we did a bunch of these where, you're going to end up using Newton's second law. So you say summation of f of x is equal to ma. For it to be a differential equation, you have to think about a is equal to dv over dt. So then I go back and they tell me here what the force is. So the force was beta v squared. And so because it's frictional, it's going in the opposite direction. If I pull to the right positive, friction goes in the opposite direction. We have minus beta v squared is equal to ma, which is dv over dt. Okay, so this is the part where you're going to end up making it look nice, like a nice differential equation. And then I think in the next part, they're going to have you solve the differential equation, which means you have to separate all the variables. You want to have, remember, you want to have, you know, the v's on one side and the t's on the other side. All right. And they're probably going to ask one. Oh, and then they ask the graphs. And they just love graphs on the AP exam. So again, look carefully at the graphs. Sometimes they do something you've never done before. So we have position as a function of time, velocity, and acceleration. All right, the third FRQ is very, very basic question, even though it's rotation, which they're going to test on. Basically, if you look at the whole thing, you're going to be thinking of a couple of things. First of all, you can do conservation of energy. Okay, so the total energy here is the energy here, is the energy here. Okay. So here, if it's at rest, again, we would have gravitational potential energy. And then it's going to go down here so I can figure out the speed, and then it's a projectile. Now this is going to roll down the table. I think this one rolls. So because it rolls, just go like this and cover this with your hand and say, you know what? We did a bunch of problems where I had, you know, whatever shape, whether it's a sphere, a cylinder, or a hoop, rolling down an incline. And when it's rolling down the incline, not only does it have translational kinetic energy, it also has rotational kinetic energy. So again, you can do conservation of energy between here and here, and then once you find the velocity here, you just cover it with your hand, and this is the projectile being launched horizontally. This is a very classic problem, and then tomorrow what I'll do is we'll go over each of these individually. That's it. So this was just kind of like an overview. So when you look at the problem, how do I set it up? You know, and because you don't have a lot of time to think when you're doing that.